they say which of the 1,000 it will be, then all 1,000 will happen. Yeah, you can laugh at it and say, well, that has to be wrong. But there are so many other things in physics which at the time that people came up with had to be wrong, but it wasn't. You have to be a little careful, I think, before you say this is clearly wrong.
And even in our own universe, quantum mechanics says there's a chance that things we'd ordinarily think of as impossible can actually happen. For example, there's a chance that particles can pass right through walls or barriers that seem impenetrable to you or me.
There's even a chance that I could pass through something solid, like a wall. Now, quantum calculations do show that the probability for this to happen in the everyday world is so small that I'd need to continue walking into the wall for nearly an eternity before having a reasonable chance of succeeding. But here, these kind of things happen all the time.
You have to learn to abandon those assumptions that you have about the world in order to understand quantum mechanics. In my gut, in my belly, do I feel like I have a deep intuitive understanding of quantum mechanics? No.
And neither did Einstein. He never lost faith that the universe behaves in a certain and predictable way. The idea that all we can do is calculate the odds that things will turn out one way or another was something Einstein deeply resisted.
Quantum mechanics says that you can't know for certain the outcome of any experiment. You can only assign a certain probability to the outcome of any experiment. And this Einstein disliked intensely. He used to say, God does not throw dice.
Yet experiment after experiment showed Einstein was wrong, and that quantum mechanics really does describe how the world works at the subatomic level.
So quantum mechanics is not a luxury, something that you can do without. I mean, why is water the way it is? Why does light go straight through water? Why is it transparent? Why are other things not transparent? How do molecules form? Why are they reacting the way they react? The moment that you want to understand anything at an atomic level, as non-intuitive as it is, at that moment you can only make progress with quantum mechanics.
Quantum mechanics is fantastically accurate. There has never been a prediction of quantum mechanics that has contradicted an observation. Never.
By the 1930s, Einstein's quest for unification was floundering, while quantum mechanics was unlocking the secrets of the atom. Scientists found that gravity and electromagnetism are not the only forces ruling the universe. Probing the structure of the atom, they discovered two more forces. One, dubbed the strong nuclear force, acts like a superglue, holding the nucleus of every atom together, binding protons to neutrons. And the other, called the weak nuclear force, allows neutrons to turn into protons, giving off radiation in the process. At the quantum level, the force we're most familiar with, gravity, was completely overshadowed by electromagnetism and these two new forces.
Now, the strong and weak forces may seem obscure, but in one sense at least, we're all very much aware of their power. At 5:29 on the morning of July 16, 1945, that power was revealed by an act that would change the course of history. In the middle of the desert in New Mexico, at the top of a steel tower, about 100 feet above the top of this monument, the first atomic bomb was detonated.
It was only about 5 feet across, but that bomb packed a punch equivalent to about 20,000 tons of TNT. With that powerful explosion, scientists unleashed the strong nuclear force, the force that keeps neutrons and protons tightly glued together inside the nucleus of an atom. By breaking the bonds of that glue and splitting the atom apart, vast, truly unbelievable amounts of destructive energy were released.
We can still detect remnants of that explosion through the other nuclear force, the weak nuclear force, because it's responsible for radioactivity. And today, more than 50 years later, the radiation levels around here are still about 10 times higher than normal. So, although in comparison to electromagnetism and gravity, the nuclear forces act over very small scales, their impact on everyday life is every bit as profound.
But what about gravity? Einstein's general relativity. Where does that fit in at the quantum level? Quantum mechanics tells us how all of nature's forces work in the microscopic realm, except for the force of gravity. Absolutely no one could figure out how gravity operates when you get down to the size of atoms and subatomic particles. That is, no one could figure out how to put general relativity and quantum mechanics together into one package. For decades, every attempt to describe the force of gravity in the same language as the other forces, the language of quantum mechanics, has met with disaster.
You try to put those two pieces of mathematics together, they do not coexist peacefully.
You get answers that the probabilities of the event you're looking at are infinite. Nonsense. It's not profound, it's just nonsense.
It's very ironic because it was the first force to actually be understood in some decent quantitative way, but it still remains split off and very different from the other ones. The laws of nature are supposed to apply everywhere. So if Einstein's laws are supposed to apply everywhere, and the laws of quantum mechanics are supposed to apply everywhere, well, you can't have two separate everywheres.
In 1933, after fleeing Nazi Germany, Einstein settled in Princeton, New Jersey. Working in solitude, he stubbornly continued the quest he had begun more than a decade earlier to unite gravity and electromagnetism. Every few years, headlines appeared proclaiming Einstein was on the verge of success, but most of his colleagues believed his quest was misguided and that his best days were already behind him.
Einstein in his later years got rather detached from the work of physics in general and stopped reading people's papers. I don't even think he knew there was such a thing as the weak nuclear force. He didn't pay attention to those things. He kept working on the same problem that he had started working on as a younger man.
When the community of theoretical physicists begin to probe the atom, Einstein very definitely gets left out of the picture.